Unit Operation Classroom. Today we are discussing determination of packed column height using the concept of transfer units. A gas stream with 2.01 mole percent ammonia. So this should be like air containing ammonia. The ammonia concentration is 2.01 mole percent. Is to be scrubbed in a countercurrent isothermal packed bed absorber. So this is something like this. So there is a packing here, and the air containing or the gas containing ammonia enters here, and of course it just goes out from here, and the water uh, is sprinkled on the top, and it of course comes at the bottom. And during this process, water absorbs ammonia from this gas stream here, and the lean gas, which contains the less concentration of ammonia, comes out from here, and the water, which is sprinkled over here, comes out here with a much higher concentration of ammonia. So basically, this is stripping the ammonia from this incoming gas stream. And according to this problem, that's 2.01 mole percent of ammonia is entering here. And this is a counter current. Of course, this is counter current here. So this is counter current. Isothermal, that means temperature is constant. Packed bed absorber using pure water. And the concentration it will come out from the top would be 0.01 mole percent. Assuming dilute conditions apply, of course, this is a low concentration. So assuming that there's a dilute concentration apply, which means that the equilibrium line and the operating line would be linear or straight lines. And the mass transfer coefficients are constant throughout the column. So basically here, on the packing, there is absorption of ammonia from the gas phase to the liquid phase. That means to water, and this mass transfer coefficient is assumed to be constant. The liquid and the gas flow inside the absorber are 1200 kilomole. So basically per hour square respectively. So this is basically 200. So 200 kilomole per meter square of the cross section area per hour. So let's call that, and this is of course 1000 kilovolt per meter square of the cross sectional area per hour. So that's the flow rate of the gas and water. The equilibrium relationship is y is equal to 0.9x. Normally because there's a y star is equal to 0.9x, which means that on this packing here, so there's a lot of packings here. So if we consider each individual packing, on the packing there of course there'll be a layer of water on it, and here from the gas phase to the liquid phase there will be a transfer of ammonia from the gas phase to the water, and of course that water drains down and goes to the next level of the packing, and slowly it just trickles down along the pack bed. Okay. So here y star is 0.9x. So basically what I said here, so if we assume this is here, so at this gas liquid interface here, this is water, and here's a bulk gas phase, and there's a gas liquid interface here. That's where we are assumed equilibrium to apply, and that is a relationship. Okay. Um, Under these conditions, the height of the overall gas transfer unit, will discuss what is meant by that, or what are the implications made by HTOG, and the number of overall gas transfer in TOG. There are different types of gas transfer units. This is based on the overall driving force, and you will get that in any standard textbooks, what's meant by that. So this NTOG, or the number of overall transfer units. So what is the concept of height of a transfer unit and the number of transfer units? We'll see that is given by basically this relation. So NTOG is given by this relationship here, where there's Y1 and Y2. So this is basically, let's say we normally take this was the level 2, and let's say this is take 1. So here the water entering, the concentration of water, concentration of ammonia in the water is taken as X1, and the lean gas which is going out is Y1. Okay, so this is equal to 0.0001, and here of course this is level 2, so this is the mole fraction of ammonia in the gases which is entering is 2. So this Y2 is equal to 0.0201, and of course from here the ditch containing water, that particular stream is coming out from the bottom. So this is called X2. So this is X2, Y2, and this is X1, Y1. So this integration is between Y1. So the integration is between Y1, that means from the bottom to the top. Okay, so this is from 0.001 to 0.0201. That is how we determine the number of overall transfer units. The integration is performed between the two ends of the column, as we said, and Y star is the equilibrium mole fraction. So this is the Y star is the equilibrium mole fraction in the gas phase, corresponding to the composition of liquid at the corresponding location. As I've said, that here at each level there might be some packings, and for that, yeah, at each level. So if this is, let's say, y2, and this is x2, and if this is, let's say, x1, and this is y1, and so at any point, if we assume that's liquid water coming out concentration, ammonia concentration x, and the gas entering is y, so this is a relationship y star is equal to, so we can say y star is equal to 9. Equilibrium relationship is given by y star is equal to 0.9x, where x and y are the actual concentration. X and y, the concentration of ammonia in the liquid phase and concentration of ammonia in the gas phase. So which one of the following is the minimum length of packing necessary to achieve the desired scrubbing? So this is a very detailed, or rather detailed, slightly description of this problem. So we'll go into it. So this is basically my absorber here. As I said, this is the inlet gas coming in. This is Y2. This is Y in is equal to 2.01 mole percent ammonia. So that is 0.0201. And this is Y1. As I said, this is the 1 and this is 2 here. This is 1, 2. So basically, this Y1 is Y2 is 0.01 mole percent ammonia. So that is 0.0001. And now this is pure water, which is coming in from here. So X1 would be equal to 0. And of course, from here, the water with dissolved ammonia coming out. So X2, we do not know, but this can easily be found out from the mass balance or the component mass balance or the mole balance. Here, G is equal to 200. So this is the flow rate. G is equal to 200 kilomole of the gas containing 2.01 mole percent ammonia per meter square of the cross-sectional area of this packing and per unit time. And similarly, L is equal to 1000 kilomole per meter square per hour unit time. Okay. So with the pack bed, this could be like Rashi rings, Paul rings, structured packings here. And this is, as we said, is a counter current. This is a counter current pack bed absorber here. And of course, we have to find out what to be the height of the packing that will achieve this desired objective. Okay, so let's go to the next level. First, we have to determine the operating line, of course, which can be obtained by solute balance. So let's say anywhere here, if we draw a line, so let's say this is the Y gas phase concentration of ammonia, and X is the liquid phase concentration of ammonia coming out. So if we do the if we do the mass balance, so from that we can find out what is the operating line. So G times Y minus Y out is equal to L times X minus X in. So basically, this is what here. So this is concentration mole overflow. This is L, and let's say this is equal to G. And anywhere, let's say this is X and this is Y. So basically, and this of course is G going out, and this is Y1, this is X1, and this is X2, and this is Y2. So what we are saying is L times L minus X in. So L times this L times X. So this one X minus X in. That means this one X1 would be equal to G times Y minus. So what is going out? Y minus Y out. That's overall balance. Okay. So from there we can get the operating line. So this is basically substitution of the values here. We know these values. So we can get, this is the equation of the operating line. All the details are given here. And this, of course, is the equilibrium line. So what we can do, we can say Y star is equal to 0.9x. And of course, this for the x, we can substitute it here. And therefore, this is equal to Y minus 0.1. So we can get This is where we put the value of x. So we get y star is equal to this equation here. So in terms of y, so this relationship basically determines what is this one. So anyway, what is the value of y and what is the value of y star? That means the hypothetical equilibrium concentration corresponding to the liquid concentration or concentration of ammonia that is coming out. Okay, so that's basically this relationship here. So this is the equation of the operating line, and this is in terms of y and x, and this is of course the equation of the equilibrium line. Okay, so once we know that, so we can easily find out what is y minus y star from here. So we can say y minus y star. Y star, of course, we can take it from here. We put it right here. This y star here. So we get this as equation of that. So this is y minus y star, which is the driving force. That means the actual concentration in the gas phase minus what is the y minus y star is basically the actual concentration in the gas phase minus what's the hypothetical concentration if the liquid is in liquid phase concentration is in equilibrium. So basically, that's the equilibrium concentration. So NTOG is given by definition is this y1 over y2. This is of course the this y in of course is the bottom of the column, and this is of course y out is the top of the column right here. So basically that's what integration what we have to do. So this is dy divided by for y minus y star we put in here this one right here, and this by integration is particularly this one where this is equal to a and this is equal to b. So basically this is an integration of NTOG is equal to integration of course y in minus y out, and we are saying dy over a plus by. And this is the standard integration. A is the value is this one right here, and B value is this one right here, and this is the integration value. So if we do that, if we substitute the values, this is shown again in this website, you'll find that NTOG is equal to 6.227. Now, HTOG is already given. We'll try to discuss a little bit about this concept. And NTOG we have given, that's number of overall transfer units. That means the transfer is based on the overall driving force. So this is already given. This we have decided. So that's 4.98. So that is 5. So basically, that's a 5 meter of height is required to achieve this desired. So this height is required as 5 meter. Z is equal to 5 meter to achieve the desired change in concentration. So if we go here, B is of course the correct option. Okay, now let's look slightly beyond that. This is what I have shown how to do the integration here. This is very standard, and this is given here in the website. Now let's try to see the graphical method. We can do the same thing in a graphical method in a slightly different way. This is just for academic inquisitiveness or academic interest. We say equilibrium line is given by this one, this equation. So for the equilibrium line, we'll draw the equilibrium line. For drawing the equilibrium line, of course, we will first find out for x is equal to 0 and y is equal to 0. So let's say this is x and this is y. So this is 0, 0. Of course, this is an equation with the slope of this one, but there is no intercept. It will start from 0, 0. And of course, this will go from here. So one point would be 0, 0. And another point, I've just arbitrarily chosen a value. Any points, any point I've taken arbitrarily chosen a value and the corresponding value 0.267. Okay, this could have been any other value. This could be like 0.02, 0.01, whatever. So just to get 2 points. So 1 point we already know. Another point I have taken this one. So you can basically draw a straight line. So the equilibrium line can be drawn as a straight line between these 2 points. Okay, and the operating line is of course given by x is equal to 0.2 minus 0.001. We have seen that before, which is right here, which is this is the operating line. Okay, we have seen this relationship. So what we can do, if this is the operating line, we have to, since this dilute solution, we said it will be a straight line. Of course, there will be an intercept and slope. So basically, for x1 is equal to 0, y1 is equal to 0.001. So that is between This operating line is between this point 1 and point 2 here. So point 1, of course, this is, remember, pure water, and this is 0.010 going out, and x2 is equal to 0.004. How do you find out? Just from this operating line, corresponding to this gas, basically corresponding to this gas here. So if we do the overall balance, so we'll get this, the liquid, the water that is coming out, concentration or the mole fraction of ammonia is given by this one. So basically, the operating line will be between the inlet and the outlet. This is the inlet and this is the outlet. So we can draw the equilibrium. So we can draw the equilibrium line. We can draw the operating line. Okay, so again, this is the same diagram here. So this is 0.004, which could opt in from mass balance or from the operating line equation. So if you do that, as you can see, this is my equilibrium line drawn between 0, and of course 0.026. And so I have just taken this value and determined what the corresponding y value is. You could have taken any other point, just we have wanted to draw a straight line. And similarly, the operating line is between, this is, remember, this is the top of the column, and this, of course, is the bottom of the column, x2, y2. So these are the 2 points. So we already know. So we can draw this line from here to here. Okay, at any particular point, the difference between y minus y star, difference between y minus y star is, of course, the driving force. So the driving force at the bottom is 0.0165. Driving force at the bottom is 0.004, minus, of course, corresponding value 0.0036 right here. So that's the driving force at the bottom of the column. And similarly, at the top of the column, the driving force is 0.01 minus 0. So that's the top of the column. So that's driving force, as you can, is changing quite significantly from the bottom to the top. So this is my equilibrium line, and this is my operating line. Okay, so we have to do the graphical evaluation of the integral, this one right here. Okay, y minus y star. We already know what is this y star. We know what is y minus y star. So basically, how do we do the integral? If we just plot 1 over y minus y star over y, so basically whatever the curve, so if we find out the area under the curve, if we do this plotting, 1 over 1 minus y star and y, so that would be, of course, the value of this integral. So for different values of y from top to bottom, we have calculated this is the function of fy. So this is the one right here. So we have calculated these values here of 1 by 1 minus y star for different values of y from 0.001. Remember, that is from the top of the column, and this is the bottom of the column. Okay, we have taken 11 points. So basically, that gives me 10 intervals. 10 intervals here. And we denote this as f0. The first one is always f0. Remember, this is never f. This is not f1. This is f0, not f1. Then, of course, applying the Simpson rule would be difficult. I'll show you. So this has to be f0, and then f1, f2, f3, so all the way up to f10. So this is the kind of the plot what we get. So this is the top of the column, and this is the bottom of the column. When the gas is entering, this is what the gas is going out. Okay. So if we do that, use Simpson's rule to do the integration. So what is the difference? The step difference is, of course, 0.0201. So my bottom minus top divided by 10 intervals here. So of course we have 10 intervals here. Okay, so this is my step size here, and the value of this integral, of course, is going to be, that's a force using Simpson rule to perform the numerical integration. This would be first where h by 3. We have found out what is this h. So the value of the first and the value of the last. So first we take this as it is, value of the first, value of that, f0 and f10. Okay, f0 and f10, first and the last. Then 4 times the odd points. That means 4 times values of the odd points. That's f1, f3, f5, f7, f9. Okay, so this is what 4 times value of the odd points and 2 times value of the even points. So even points would be f2, f4, f6, f8. Okay, we have already taken care of f0 and f10. Okay, so if we do the integration, we get the NTH is 10.33. And if we multiply it by the HTOG to find out the height of the backplate, it's 8 point. That is significant difference between the exact analytical integration and using the graphical technique. So this was 5 meter, that is 8.26. quite a difference. And this significant error resolves because of the Simpson rule. Because we have taken 10 points, had you taken 50 points, then it would have been easier. Because as you can see, the curve is pretty as a change in slope quite dramatically in this portion. So that gives rise to the error. If we increase the number of points, of course, then if we increase the number of points, then of course these two values would be very similar. What's the practical application of this problem? In an ammonia or urea plant, some vent streams may contain small amount of ammonia. As for example, ammonia storage tanks, urea granulation or peeling towers, loading and unloading stations. Environmental regulations require removal of ammonia before discharge of these streams to atmosphere. Okay. Um, Also, in caprolactam nylon intermediate interstices, there's a significant discharge of ammonia. In refrigeration plant, we do the ammonia refrigeration. There could be ammonia leak refrigeration system, so there will be some kind of ammonia coming out, which need to be absorbed in water before the vent stream is discharged to the environment. Intuitive explanation of H2. So I'll just try to give a very intuitive idea about this H2G and NTOG. Finally, the total packing height, as we say, is the height of one effective mass transfer step. So basically, this gives an idea of the height of one effective mass transfer step, and this is the total number of steps. Okay, so that's basically the height of the packing. So NTOG, as you can see, is dy minus star. If you see just kind of difference, so if we tell this is delta y, so this is the overall change in gas composition from the top to bottom. And the y minus y star is the driving force, average gas phase driving force. Remember, we have shown if this is the equilibrium line and it is operating at any particular point, the difference between two, that's my driving force. This keeps on changing, of course. So I'm just saying average, let's say, for the sake of intuitive idea. So this gives you a basic idea of the difficulty of separation. So NTO just 6.23 in this problem means about 6.23 overall gas transfer units mass transfer steps are required to achieve the desired separation. What is H2OG? H2OG is the height of one effective gas phase mass transfer step, which is 0.8. We found out the number of steps. And we know this is given by this definition, G over KYA. And smaller H2OG, of course, if small H2OG gives more efficient packing because N2OG remains same. If this is small, so we can achieve a separation in a much lower packing height. So smaller the H2OG, more efficient is the packing. So this value of H2G depends on the packing type, what kind of packings we are going to use, gas liquid flow rates, gas liquid physical properties, density, viscosity, diameter, and the surface tension. H2G is obtained from packing manufacturers normally and the pilot plant data. That's what the overall idea, solution, and the notes about this particular problem. So finally, basically, just wanted to say that this is my answer.